Hello, this is Hannah Day, and this is my Lab 5 for Physics 2211 Soup Summer 2019. To introduce this lab, I'm first going to talk about an experiment that Felix Baumgartner did. In October 14th, 2012, he rode up in a hot air in a helium balloon and then jumped out in the stratosphere and fell at a speed fast enough to break the sound barrier. He traveled at a maximum of 373 meters per second, whereas the speed of sound is only 343 meters per second. In this jump, Felix was able to break records for freefall, and he was also able to prove that a human can safely accelerate through the sound barrier. There's a whole website that has details of this jump that I included here. The whole jump was sponsored by Red Bull. So the physics principles at play here is mainly Newton's second law, where you have your final velocity is an iterative sequence where you have the initial velocity plus the net force over mass times delta t, and your force of gravity is your mass times the gravity constant, and you have a drag constant being applied to the square of the velocity to slow the fall. And then with all of these combined, you have the sum of the force of gravity and the force of drag to get your net force. So over on the right, you can see a little free body diagram where the air resistance is pulling up, whereas your weight or the force of gravity is pulling down towards where this is Earth at the bottom. A terminal velocity was also reached during the fall, and you can see this graphically on the right, where the terminal velocity is around where the line becomes linear during the fall. And terminal velocity is defined as the speed that an object reaches when the medium provides no further resistance. In this jump, Felix fell for a total of 549 seconds, where he opened his parachute at 262 seconds. So he had 260 seconds of free fall before the parachute was deployed. This is a video of the jump. So he's up here above the surface of the Earth, outside of his parachute, or outside the balloon, and then he jumps. And you can see him going through the stratosphere, through the atmosphere. There's the Earth. He does start to spin a bit, and you can kind of see that here, where he spins a bit and then is able to gain control as he falls because he is a seasoned skydiver. And then eventually he deploys his parachute and is able to land safely on Earth. I was able to use the skeleton code from Lab 2, and I changed the initial data points to have the mass of Felix with all of his equipment on, and his initial position vector, and then I changed the proportionality constant around a lot, and as you'll see in a moment, I was never able to fully get accurate results, but I did mess with the proportionality constant to try to figure out an accurate model for drag. And so you can see I have the total time of his fall, which is 549 seconds, and then you have your force of gravity, as I described earlier, and then the force of drag, where that B value is applied, and then the sum of them gives your net force as he fell. And so then the velocity and position are both iteratively calculated throughout the whole sequence of his fall. In the glow script code, I produce a graph that looks like this, which is a very oversimplified model of the fall. We have a terminal velocity over on the far right side. You can see that the position goes into negative values, which I was never able to get it up to end at 0. So when Felix fell, he first was in free fall, and then he stopped accelerating when he reached the air resistance, where he collided with the air molecules, and then because the density of the air got thicker, he ended up actually slowing down. So this became a very complicated multi-step process with the fall. And so I think to more accurately code this, you'd have to split it up into different portions of the fall where the different densities are split up and the whole loop is recalculated for each density. But this is an oversimplified version of the fall where the terminal velocity would be reached towards the end. So forces during the fall, first you have just gravity pulling him down that split second after he jumps off of the balloon. Then you have gravity with a little bit of air resistance, and then as he continues to fall, you get a lot of air resistance, and that's what starts to slow him down. So just to discuss some changes in air temperature and density, he fell through the stratosphere and the atmosphere. So temperature-wise, the temperature decreases as you go up through the troposphere, and then you hit the tropopause where things start to change, and then the air actually heats up as you get into the stratosphere because of the collection of UV in the air up in the ozone. So as he fell, it got cooler and then warmer as he fell. And then Felix actually felt complete weightlessness when he was in areas of such low air density because the density gets greater as you come towards Earth. So when he was up here, he felt very little air resistance, and then it kind of hit him as he fell down, which again would also be something to consider in coding a very complex model of his fall. And then the height to break the sound barrier. So Felix jumped from a height of 36,576 meters. An average skydiver jumps from about 4,000 meters and experiences 60 seconds of free fall, whereas Felix had a total of about 4.5 minutes of free fall. So he definitely had a longer fall than most jumpers. The one thing that makes his case unique is that gravity was the only force pulling him towards Earth. There was no engines and no other things pulling him down besides gravity. So he was able to fall faster than the speed of sound for this whole chunk of time where he's above the speed of sound as graphed here. And the speed of sound is modeled after the density of the air as he fell through the atmosphere. So another application of this is that supersonic jets are experimenting with breaking the sound barrier, and you hear a sonic boom when these planes are able to pass through the sound barrier. And some jets are actually being test dropped at about 18 miles above the surface, and you can hear the sonic boom as they're dropped. But again, these both have engines and are a lot heavier than Felix, so they don't require as high of a starting point to drop from to break the speed of sound. But Felix did in fact break the world record for being the first human to break the sound barrier with just him falling through the atmosphere. So thank you so much.